Okay, thanks for joining today's brief webinar as part of Xtralis' virtual series. I'm Wes Marks. I handle the mission critical vertical market for Xtralis. Today's topic will be on VESDA application for containment aisles. If you haven't already, I'd strongly recommend visiting our website, www.xtralis.com, and downloading our telecom and data processing facilities design guide. It covers all aspects of VESDA within these facilities in depth, including containment aisles. Air containment aisles are the norm in today's data centers as they deliver cooling to specific components that require it, as opposed to conditioning the entire space, which was previously done. Air containment is efficient and effective at reducing end users' cooling costs and power consumption. Containment aisles are created by separating hot and cold air with barriers and have many possible configurations, including hot aisle, cold aisle, collar, chimney, and in-row configurations. Before we go further, I wanted to highlight the code requirements for these areas. Per NFPA 75 2017 edition, the standard for protection of IT equipment, smoke detection is required at the ceiling level throughout an IT equipment area, below raised floors containing cables, in exhaust and return airstreams where aisle containment systems are used, in the return airstream where the above ceiling is used as a return plenum, and to operate required smoke dampers. Due to the high airflow rates in these areas, ASD technology is best suited for detection due to its sensitivity and cumulative detection. Utilizing VESDA within a containment aisle is done by placing the sampling tube along an air path exit before mixing and diluting with air from the plenum outside the containment aisle. You can see the orange sampling tube location shown in this picture and diagram. With regard to sampling port spacing at this location, open area coverage guidelines are not applicable due to the airflow patterns and velocities, as well as the typical lack of a ceiling within a containment aisle. If sample port spacing is too far apart, an incident could go undetected until the fire grows to a size at which its energy is sufficient to overcome dilution and mechanical forces of the HVAC system. For adequate detection performance, consider sample port spacing not to exceed 36 square feet, so 6-foot spacing along the center line of a hot aisle exit path as shown here. So general requirements are 6-foot spacing sample port at the exit point of the containment enclosure. In a chimney scenario as shown to the right, coverage shall not exceed 2 square foot spacing per sample port. Sample port shall be labeled and oriented down 20 to 45 degrees toward the incoming airflow. The pressure difference between sample ports, pipes, and detector exhaust shall be less than 100 pascals. And lastly, a VES detector is recommended to provide multiple zones for aisle addressability. This diagram illustrates the VES to provide a separate pipe and zone for each hot aisle. Here we have a full view of hot aisle containment with the drop ceiling and raised floor. The pipes of a VES are sampling from the hot aisle, providing up to 4 zones per VES. Our design criteria for this location is 6-foot port spacing, sensitivity at each port not to exceed 0.2% obscuration per foot for alert, and 1.0% obscuration per foot for alarm for very early warning. Transport time should be 60 seconds or less. Consideration should also be given to cold aisle open areas. This diagram shows a separate VEP detector using capillaries to sample from the cold aisle open areas. Our design criteria for cold aisle open areas is 200 square foot sample port spacing, 0.2 and 1% obscuration per foot alert and alarm thresholds at the sampling port, and a 60-second maximum transport time. For redundancy, detection at the AHU return or supply is commonly practiced. Our design criteria includes 4 square foot sample port spacing at the grill area, 0.2 and 1% obscuration per foot, alert and alarm thresholds at the sample port, and proper orientation for the sampling ports at 20 to 45 degrees towards the incoming airstream. Consideration should also be given to areas where combustibles are present per NFPA 75, within ceiling and floor voids. In-row cooling technologies is based on deploying cooling units alongside servers in the cold aisle, bypassing the need for a raised floor. The goal is to shift cooling from a room-based approach to a row-based approach. Cooling units are directed toward each other such that they build up static pressure in the cold aisle. Our design guidelines for in-row cooling includes sample port spacing at 4 square feet at the return grill areas, 0.2 and 1% obscuration per foot alert and alarm thresholds at the sample port, and proper orientation for the sample ports at 20 to 45 degrees toward the incoming airstream. Thanks for watching today. Once again, I strongly recommend downloading our design guide, and please reach out if I can be of assistance with your project. Thank you.